Hello. So, again, my name is Rebecca Larson, and I'm going to be talking about witnessing the birth of stars using heat vision. And so I think the first thing I need to address is what is infrared?
Capturing the heat instead. There is light from the sky that we can't see in the darkest parts of the galaxy. With Spitzer's spectrum we can detect them easily.
Isn't it the worst thing you've ever seen? I love it. Okay, so infrared. Of course, I think Steve told everybody exactly what I'm going to talk about. So infrared, why do we care? Infrared is longer than visible wavelengths. So if you looked out into space, you would see, if you had Hubble eyes, what the Hubble sees. But what we're going to talk about is infrared light, which is actually heat signatures in space. So the wavelength is a little bit longer. And what that means is that when you look at where the brightness of infrared light peaks, it's in temperatures that are cooler than the sun. Like we see the sun in visible wavelengths because you look outside and you can actually see the sun. But I don't know if anybody's ever used heat vision goggles or played a video game where you have night vision and you can see people light up because they emit heat. So it's the same idea. So I went to NASA's website and I was like, okay, infrared, what's your biggest example of infrared? This is what it is. That's terrifying. We're going to move on. Okay, so different wavelengths will show us different things in space. So when you look in the very middle, there's a laser pointer, I think. When you look in the middle here, this is what Hubble would see. This is optical wavelengths. So again, if you looked outside with your eyes, if you had telescope eyes, which would be awesome, you would see this. But X-rays show you hot gas. Ultraviolet shows you hot, brand new stars. Infrared, which is the coolest, by the way. Infrared shows you cold stars, dust, and gas. And then radio is going to show you the cold gas. So this is the same galaxy looked at in multiple wavelengths. So clearly there's a lot of information out in space that we're missing out on if all we look at is visible wavelengths. So infrared is important, which is why we're building all of the telescopes in infrared, and not just for high redshift galaxies. So this is our Milky Way. So if you didn't live in Austin and you've lived somewhere else where there was not a lot of light pollution and you looked outside with your own eyes, well, this is a little bit prettier, but if you looked outside, this is what you would see of the Milky Way. And you can see all of this dark spot right here, all of this darkness is actually dust that's blocking the light of the stars from the center of our Milky Way from getting to you. So you can't see through dust, just like you can't see the sun through the clouds outside because it's lovely weather. It's the same idea. But if you wanted to look at the infrared, you actually get to see a whole lot more of what's going on. So this is the near infrared. So what you're looking at is slightly longer wavelengths than what your eyes can see. And you're tracing all of the gas that's forming stars here. So the other picture we had was actually face on. So you have the spiral and you can see, but since we're in the Milky Way, we can't actually see the spiral part of it. We have to look through it. So we're oriented on the side. So if we look towards the center, this is the center of the spiral and the whole thing spirals around. You can imagine it spiraling around in this direction. And we're looking straight through that. So if you look in the far infrared, you actually get to see a lot more of the dust and the gas that's all around the Milky Way that you just can't see if you don't look in the far infrared. So there's a lot more information out there. But we have to go to space. And again, Steve stole my thunder. But you have to go to space because the atmosphere actually blocks the light. The particles in the atmosphere interact with the light and the infrared as it comes through, and so we can't see it from here. So this is the visible light, which obviously we can still see the sun, like I said, which is peaking in the visible light. If you go into the infrared, it doesn't quite reach the ground, so you have to actually send, this is Spitzer, it's a cute little picture, you actually have to send a telescope to space to get past the atmosphere. You can send airplanes with telescopes out the side of them, because that's a real thing. But it's better to go to space. It's a little bit more expensive, slightly. actually not that much more expensive than our stupid telescope on an airplane. But radio waves reach the ground, which is why we have big radio telescopes. And if you ever see Contact, that's exactly what that's about. So go watch that. Shameless plug. So what telescopes do we have currently that operate in the infrared? Currently, I should probably not say currently with the next slide. So the Spitzer Space Telescope, it was launched in 2003, and it operates in the near to mid infrared. So shorter infrared wavelengths. So that first picture of the Milky Way I showed you when I switched to near infrared, that was taken with Spitzer. So it can also take pictures, and it can take spectra. And that means that we can just image things in the infrared, and we can also measure the light from specific wavelength ranges. So Spitzer actually is not that big, but it trails the Earth in its orbit about 66 million miles behind the Earth, because again, just like with James Webb, we have to get away from the influence of the heat and the light of the sun, the Earth, and the moon, because we as humans emit in the infrared, so does the Earth, and so does the moon, and obviously so does the sun. So we need to block some of that light, so we need to keep the instrument cool so it doesn't detect itself. We need to keep it far away from us so it doesn't detect us, because what we really want to look at is space with a telescope. So it actually has coolant that cools it down, which is out now. So it just operates in the warm phase. So it's in the shorter wavelengths, but it's still cool. It's still out there. And then here's my favorite telescope. This is the Herschel Space Observatory. It was actually a joint mission with the European Space Agency and NASA, and it's actually operated by the European Space Agency, which is why probably most of you haven't heard of it, even though it's really, really awesome. I mean, just look at that picture. Isn't that pretty? That was taken with Herschel. So it was launched in 2009. It operates in the far infrared. So these wavelengths actually are the wavelengths at which the dust emission in space peaks. So if you want to look at dust in space, you need to go into the far infrared. So again, it can both take pictures and it can take spectra. And it's really the first telescope that we had that operated at these wavelengths, because it was the only one that was out in space and doing this. And it's dead. So it ran out of coolant. It was out where James Webb is going to be out at L2. And it ran out of the coolant. And because it was only so big and the resolution wasn't so great, and the coolant is out, we haven't replaced it. And I don't know when that's going to happen. So we can talk about future telescopes for far infrared. So I'm sure a lot of you have seen this picture. This is probably one of the most famous Hubble images. They actually went back and re-imaged it recently in the higher resolution that Hubble has. And this is called the Pillars of Creation. It's in the Eagle Nebula. And what you're looking at, if you look at it, is a bunch of dust in space. And you can't see into it, into what's happening inside of it. But if I can get over here, you can kind of see the light shining out from behind these clouds. So you can see that there are stars and things happening inside this cloud of dust and gas that you just can't see, but you can see the effect of them as the light shines out through like little holes in it and that kind of thing. So this is actually where star formation happens in molecular clouds in galaxies. So this is where all of the activity really is. But we can't see it in the visible light because all this pesky dust is in the way. So this is my favorite image. That's what it looks like in the infrared. That is all of the information that we are missing by just looking in the visible. So there's all of these extra stars. You can see inside of it. And this is near infrared, so again, you're kind of missing some of it because it's blocked by the dust. But you can see through it, and you can see these stars forming. And that's actually really interesting because, I mean, we are here because stars formed and a planet formed around a star, and that's how we got here. So we want to figure out how that happens, and the only way we can do that is to study things in the infrared, because we have to be able to see through the clouds of dust and gas that form stars. So this is that same picture, kind of tilted because, you know, there's no down in space. So this is that little cutout image that I had earlier. Those are the pillars. And you looks like you're kind of looking into a cavern. There's some space in here, and looks like a whole lot of nothing out here, and some stars. And just looks like stars are forming right here because there's all the dust and gas, and you can see kind of some of it on the edges. And this is what you see when you look at the Eagle Nebula in the visible wavelength. But again, I would argue that far infrared is really important, because if you want to actually look at what's happening and stars are forming, you need to look at the heat signatures. So these stars are forming in these clouds, and they're very hot and they're very bright, and they actually show up in the X-ray, but they heat up the gas and the dust around it. And so if you look at those heat signatures, and you can look at the heat signatures in space, this is what you actually get to see. There's all this other information and all this other structure out there in the universe that you're missing out on if you don't look in the far infrared. And so this is actually taken with Herschel. This is the best telescope. But you can see that this is a big cloud of gas and dust, and this is just a little pocket that we can see through because all of the stars that formed here have used up that gas and dust making stars. So the way that you make a star is you take a cloud of dust and gas, and through some time in physics, it starts to collapse under its own gravity because it gets dense enough. And then it starts to spin up, and then that flattens into a disk, and then that disk gets carved out by planets, and it's a whole process. So what we need to find out is, how does that happen? What are the clouds like before that starts to happen? And when and how often does it happen? Because if we can learn that information, and we can learn how we got here, how long it took us to get here, and maybe what the right type of environment is to create another solar system, to create another Earth, or to create another star like our sun. So again, I guess I should show that picture. So this is that same idea. This is another image taken with Herschel, where you see all of the clouds of dust and gas being heated up by these stars that are forming. And this is what's actually happening, is the cloud is compressing into a disk with a star inside, and that starts to spin up and use up all the gas, and it falls in. You get these little pockets where it's used up the gas and dust to make those stars, which we would need to see in the infrared. And this is really cool because planets are cool. And this is what you would see with Hubble. So this is the longest wavelength that we can get Hubble to look at. And you can see that we tried to mask out the light of the star. And you can see that there's a star here and there's a disk, which is forming around it, which is where you would find planets forming. This is a pretty famous object, Fomalhaut. For a long time, we thought there was like a little dot right there. That was the planet that we actually took a picture of, which hadn't happened yet. So we looked at it with Herschel, and you can see it's all heated. The star is hot, and it's heating up all of that debris that's around it, and it's really bright right here because this is actually like a bunch of comets that are flying around it, or pieces of dust, or planetoids, or whatever you want to call them, that are crashing into each other and maybe forming a planet. But we'd have to watch for hundreds of millions of years, and I don't think I have time for that. So this is ALMA. We actually see it in the radio, and I'm not going to talk too much about that. But that's also one of our big radio telescopes, and we can look at the cold gas and dust that's around the area right here. And I think we find that is not actually a planet, which is disappointing, but it's great that we can have that kind of knowledge now, that we can take this image and we can see this object we take at different times, and it looks like it's actually just an object passing through the system or in front of us, or it's just not rotating at the right orientation. So just to compare what we're looking at, this is this system that we imaged with Herschel. And this is a comparison to the size scales of our own solar system. So this actually is one step closer to finding systems similar to our own. So that's great. Why do we care? So dust and gas are great to look at. We have to use infrared because they're only in heat signatures. They don't emit their own light. And so what we want to know is how much dust and gas are in galaxies, because if we measure that, we can measure how many stars they're forming, and if we measure how many stars they're forming, we can measure how many planets there are. We could maybe find other civilizations like our own, or we can just learn more about how our galaxies evolved into what they are today. So we can look at higher redshift galaxies, find out when they form stars the most. We can look at galaxies closer to us and find out how many stars they formed, and figure out where we are in our succession of building stars and planets and all other kinds of things. So I've showed you a lot of really pretty images. These are my last set. So this is Hubble Imaging of some galaxies. And this is a project that I worked on where we're looking at a cluster of galaxies. So these are galaxies that are all really close by each other. And this is the big bright one in the center. And they're actually lensing things, which is what MC Hi-C works on, is galaxies that are lensed. So you have this huge, huge group of galaxies that are very massive. And they are actually so gravitationally strong that they are bending the light from objects around it. So you can see things far away and behind these clusters of galaxies that you couldn't see without this effect from the gravity. And what I was looking at was not the cool part of the lensing, sorry, but I was looking at the galaxy in the very center of this cluster. So these are the most massive galaxies in the universe. They've had to hang around long enough that they've built up enough mass. They've been moved to the center of this cluster and pulled all these other things around into them. And they are supposed to be pretty old. And as a galaxy gets old, it uses up all of its gas, it uses up all of its dust in making stars, and they just kind of hang out for a while. It's not building anything new. It's pretty stagnant. But what we were seeing when we looked with the Hubble Space Telescope was that you can see some filamentary structures, which is a fancy term for the little stringy parts that seem to be falling into the middle. And you can see that it looks like gas and dust are being pulled out of the greater assembly of galaxies in this cluster into the center galaxy. And so what you need to make stars, like I said, is gas and dust. And so if we're putting a bunch of gas and dust or pulling in even more from the surrounding galaxies, we're creating stars. And what they find when they look with Hubble is they can count the stars that they see, because stars emit light in the visible. So they measure the amount of stars that they see, and they say this is how many stars it forms every year, and it's in solar masses. So we want to use units that make sense to people when you think about it. So a solar mass is how big our sun is. So they make so many suns per year. In comparison, our Milky Way makes about 1 to 2 sun-sized stars per year. These galaxies, when they counted them up and then guessed at how much gas and dust that there was, were making about 300. And these galaxies are supposed to be dead, meaning they're not supposed to be making stars anymore. If they're making stars, they're not making them very often. So this seemed like a very high number. And they thought, well, that can't be right. What do? We point the Herschel Space Telescope at it, and we actually measure the dust. So you measure the amount of fuel that you're providing these galaxies to make stars, and then you can measure the stars that you see. You can measure the fuel that they have to make stars, and then you can add the two things together to figure out how many stars they're actually making. And so that was my job. So now I told you I showed you all the pretty pictures. This is what I actually look at. Isn't that pretty? So that image before was 16 different images taken with the Hubble Space Telescope at different wavelengths. And I'm just going to use one of them for reference. This is probably the least high resolution that you're going to get with Hubble, and the near infrared. And this right here is that bright galaxy in the middle that's kind of blurry at this wavelength. And then this is kind of the cluster around it. But again, it's not the best resolution. It's definitely not as pretty as that last picture. So the Spitzer Space Telescope that operates in the near infrared is these two images right here. And so I need to make sure that I'm comparing apples to apples, so to speak. And I want to make sure that I'm pointing the telescope at the right galaxy. And then I have to measure the amount of light in each image. So the resolution with Spitzer gets a little bit worse, because the size of the telescope compared to the wavelength of light that it looks at determines the resolution. So if you have a longer wavelength of light, you need a bigger telescope to get the same resolution. So with Spitzer, it's not too much worse, but if you're looking with Herschel at 100 to 500 microns with a telescope mirror that's about 3 meters, you need a little bit more resolution than that. So the struggle with comparing things is that if you had the same resolution and you could decide this galaxy with this resolution at this wavelength is exactly the same galaxy as this little bright pixel, I guess, you can actually compare the light. But the problem is that with a longer wavelength, you need a bigger mirror, which is why James Webb is going to be bigger, which is why HGST is going to be bigger to get a higher resolution, because you have a longer wavelength and you need a better resolution to do the same type of science. So when I actually look at these pictures, what I have to do is figure out how much of that light is from the galaxy I'm looking at and how many of the pixels are actually contaminated by the light of other galaxies. So what I've drawn on here is actually the smallest resolution or the smallest aperture measurement that I can make for each wavelength. So just as a comparison, this is the Hubble image, and this is the best resolution I have with Herschel. And this is the worst resolution I have with Herschel, and this is the Hubble image. And I don't know if you can see it right here, but this is the size, the smallest measurement I can make at 500 microns in the far infrared is the size of the entire cluster of galaxies. So I have to figure out some way to make sure that I'm just measuring that one galaxy, so that I'm accurately measuring the light from that one galaxy, the stars forming and the dust and gas in that one galaxy, so that I can determine how many stars and how much fuel it has. So that's a complicated process, and we decided the best way to do that is to do some physics and measure the amount of light in a big circle about this big around each image, and then kind of correct for that. Because the beauty of this is that with Hubble, we knew a lot about the galaxy already. We knew where it was, we knew what was around it, we knew how far away it was, and so we were able to determine a lot of the properties of this galaxy before we could even make the dust measurement. So I knew that none of the other galaxies in that cluster had as much dust. So I could say that this bright pixel right here, that's pretty much just my galaxy, because none of the other ones have enough dust to be that bright in the far infrared. So because I'm a scientist, I have to show you a plot. So this is actually the light emitted by a galaxy at multiple wavelengths. So right here is the UV and the visible wavelengths of light. This is where you see stars. So if you actually look at the Hubble images, these are all the measurements they took with Hubble. These are the measurements of Spitzer. So this is the infrared looking at the the gas, and then these are the little data points that I made. So you can see that this is the amount of dust, and this is the emission of dust in the galaxy. This is the actual heat that is emitted by the dust particles that are forming stars. So if we just have these data points, we have no idea if this is up here or if it's down here or how much dust there actually is. So it's really important to have that information. You can guess. And they did guess, and they got a number that was absolutely insane, and they thought that can't be right, so let's actually measure the dust. And so they were lucky enough to get Herschel time before it died, and then I was lucky enough to get to do these measurements. So this is what you get when you plot the luminosity, so how bright is this galaxy at each one of these wavelengths, and then figure out through some other more math-involved things the total luminosity or the total brightness or how much light this galaxy is emitting overall, and you can measure star formation rates that way. So of the two galaxies that I showed you, this is the measurement that they made with the Hubble Space Telescope. They counted up the stars, and they said this is how many stars there are, and this is how many they make per year. And then this is how many they guessed were going to happen right over here, is they estimated the dust based on properties that they had, and they thought 276 suns per year in a galaxy that's supposed to be dead. That can't be right. So then I actually measured the dust, and you see that there's a whole lot. Like if you actually add the measured visible light and the measured infrared light, you get a really big number. So that's still crazy, right? That's still not right, obviously. But it is. And so the importance of these far infrared observations show that even though we get crazy, insane numbers that we don't expect, they can still be right. Just because we don't think that they should happen doesn't mean that they don't happen. So for the future, when we don't have a far infrared space telescope, we have some kind of model to show that when we're doing these corrections, we're making these estimates when we just have visible data, we just have near infrared data, we can still get accurate measurements of how many stars these galaxies are forming. So that means that maybe we don't understand the physics of how this is happening. Maybe we don't understand exactly how stars are forming in this environment. But at least now we know we have a number to use. So infrared's really important to keep using, even though Herschel's dead. So James Webb, which you guys just heard all about, is going to be the future of that. So it's not just for high redshift galaxies. It's not just for the furthest things in the universe, but it can also do some amazing things, like measuring all of the dust and the heat signatures in space, and to figure out how much gas and dust there is in these galaxies, or how much gas is around a forming star, so we can figure out how that happens, and better resolution because we have a bigger telescope, so we can determine exactly what we're looking at. And so there's a lot of capabilities of James Webb, and I just want to leave you with one thought to kind of contradict Steve here a bit. Space dust is the coolest. It's the coolest thing. And I don't mean just temperature. I mean it really is. So this is that same image. Oh, God. Go back. Aw. I got this. Okay. So, yay. Thank you. I can use PowerPoint. This is the visible light, like I showed you before. This is that infrared picture I showed you. This is what you see when you look in the X-rays. So these are all of the stars. This is a composite of all the three. These are all of those stars that just ate up all of this gas here in this little cavern of this cloud here. You can see they all formed, and they're very hot because they're brand new and they just lit up. But they heated up all of this stuff around them. So we can see in the infrared because all of these stars just formed. And so you can see, again, these are really cool. Just the whole thing is really cool. So it's important. Thank you.
Time for just a couple of questions. First one comes from Twitter. How does one lease time on a space telescope? Can I rent it and take pictures of space on my own?
So on a normal telescope, there are some that you can purchase time on, and it's not exactly cheap. So, but if you want to buy time on telescope, come talk to me because I will definitely use it. But space telescopes, you actually have to write this proposal, and you have to say, my science is really important, and I should get time over everybody else who's asking for time, because there's really only so much time that you can operate a telescope. And then it goes to a committee of scientists who are specialists in that field, and they go, yeah, that science seems like it's really important, and really this is the telescope that you have to do it, and you do have to do it because science. And so you have to fight for it.
All right, one more question for Chaos Cloud. Right there.
So all of these images that you're showing, which are infrared, but you see pictures, so are they translated into visible or
So the question was, I'm showing you pictures of infrared wavelengths, which I'm telling you can't actually see. So what's that about? So it's false color. So they assign a color to a wavelength, and then they assign a different color to a different wavelength, just to give you a visual of what you're looking at, so you can see the difference between the brightness of one wavelength versus another. It's the same way that visible wavelengths of light work with your eyes, but we just assign it a color, and whether or not I agree with their color scheme is not the point, but it's just to show the difference in levels of light, so you can see the actual structure that's there.
All right, let's thank Chaos Cloud one more time.